So we're given that EMF as a function of time is NBA omega sine omega t, right? And so this right here is the amplitude of the function. That's the maximum EMF. So if you want to know what the maximum voltage is, you've got to multiply those together. Now we're given N is 750 turns. We're told that the magnetic field that it rotates through is 0.81 Tesla. The area of the loop is 140 square centimeters, so that's 140 times 10 to the minus 4 square meters. Right, and now just in case you're still having trouble with this, right, the way we make that conversion is we multiply by 1 meter over 100 centimeters squared. So it's 140 divided by 100 squared. So that's 140 times 10 to the minus 4. Or if you, I guess if you'd rather, it's 0.0140 square meters. And then omega, well, we're given the angular frequency. It's 45 revolutions per second. But we've got to get that into MKS units. So I got to multiply by 2 pi radians per rev. And that's 283 radians per second. So pretty fast. Okay, so I've got N, I've got B, I got A, I got omega. If I multiply those quantities together, and they're all in MKS units, I get 2400 volts for this generator. Okay, so there's part A. And part B, so the area vector is perpendicular to the external field or parallel to the external field when this maximum voltage occurs. Well, let's think about that, all right? So when the area vector is parallel to the magnetic field, that would be an example like this, where the loop is in the plane of the page, and the magnetic field lines pierce the loop, and the area vector is also in the plane of the page. Okay, so at that time, phi b is at its maximum possible value, right? It has a maximum and minimum. Right? Phi b is NBA cosine omega t. Okay, and at that time, right here, omega t is equal to 0, so phi sub b is at its maximum value. And it's not changing quickly. Right? Remember that if we draw a graph of phi versus time, it's a cosine term, right? So it goes like this. And so when phi b is maximized, here, 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 and over here, at that time the slope delta phi b over delta t is equal to 0. So, so at that time, I would say that the, I guess when A is parallel to B, then I would say that phi b is maximum and delta phi b over delta t is minimum, is equal to 0. And so the induced EMF at that time would be equal to 0. It's minimized. Okay? And then, therefore, when A is perpendicular to B, that is when the induced field is maximized. Right, so that's our answer when A is perpendicular to B. Because when A is perpendicular to B, that would be an example like this, where I've got my loop like this in the plane of the page, but the field goes across the plane like this, and the area vector points into the page. And at that point, you're here, or here, or here, where the flux at that time is 0, but the change in flux, the slope, is maximized. And since the induced EMF depends on the change in flux, it would be maximized at that time.